In this video, I will talk about equipotential lines. Now, I'm gonna break this term. First, the fact that we talk about lines means exactly what the word implies. What I will be drawing is simply lines. Now, the fact that we have the part of the word here that says equi means that essentially they are lines where you have the same potential everywhere on those lines. I should say maybe not on those. I would say on each line you have the same. On each line, each forgot. All right, each line you have the same potential. I'm gonna give you an example. Let's say that I have a charge here plus Q. Okay. Now I know that the expression for potential at a point from a single point charge is the constant Q over R, where R is the distance. Now here's the thing. This is a constant. If I'm dealing with the same charge, the same point charge, then the point charge stays constant. If I want to find an equation for the equipotential lines when I have a single point charge, then by definition I will need to keep the same potential on each line, which means that V needs to be the same. So at the end of the day, if everything here is constant, then what you're left with is that the distance R needs to be a constant. Now, this is what I want you to think about. How can I start? Okay, if I start from the point charge, how can I keep a constant distance? So if I am here, for example, then a constant distance would be somewhere there. Constant distance would be somewhere there. Constant distance would be somewhere here. And I hope you can see the pattern. Okay. At all these points, I've tried to maintain a constant distance. And if you keep doing more of this, you're gonna see what the pattern is. The equipotential line for a point charge is simply a circle. Now let's do. Anyway, I don't have. Let me see if I can. I'm gonna erase these, and I will actually draw a circle. Let's see. So let's see if I can make a circle. That's pretty good. Not close. All right, it will not be a perfect circle, but we're gonna pretend that this is a circle. Now this is okay. This here. Okay, we're pretending it's a circle. For a circle is defined as having a constant radius, right? And that's why if I keep a constant radius, a constant distance from the center, then I have one equipotential line. So this is an equipotential line. Now, will this be an equipotential of 1 volt or 0.5 volts or 2 volts? Well, it really depends. Okay, I'm doing this drawing qualitatively, conceptually, but I have not done any calculations. If you actually know what the charge is and you know what the distance is, then you can even calculate whether this equipotential will be 1 volt or 2 volts and so on. Now, this is what I want to do. I want to draw some more of this equipotential so that you get a better feeling. If and another way, yeah, let's add one more equipotential, and we're gonna also pretend. Oh, look at this. This is closer to being a circle than the other one. Okay, whatever. So we're pretending also that that's another circle, and this is another equipotential. Okay, if this is 1 volt, because I'm decreasing the distance for this equipotential, decreasing the denominator means that I have to increase that. So this is gonna be, let's say, 2 volts. Okay, and then the closer you get, the higher the potential will be. The further away you go, the lower the potential of that equipotential line. The important thing, and what I want you to see from here, is the pattern. Okay, for a single, nope, I'm gonna try again. For a single point charge, oh, that's very close. For a single point charge, the equipotential lines are simply circles, and let's say that that one is 0.5, more or less. Okay, qualitatively, in general, the closer you are to the positive charge, the more positive the potential is, and the further away you go, the smaller, the lower the number is. But the equipotential for a single point charge, those lines, they are simply circles around them, with the center of the circle at the location of the point charge. Now, the why did I start with lines? Well, what I have in front of me is the two-dimensional screen of my computer, and what you are looking at is also a two-dimensional monitor. Now, if I have a point charge in the 3D space, and I'm talking about now a three-dimensional area, then around a single point in a 3D space, in order to keep the radius constant, you're really looking at the spherical cell, the surface of a sphere. So that will be the surface of the sphere. So yeah, I'm not gonna say anything different. So if you want to generalize this in the 3D space, okay, this is in 2 dimensions. If you want to generalize that in 3 dimensions, then you're really looking at the sphere, and in particular, the surface of that sphere has the same potential everywhere, because by definition, the way that you define a sphere is when you maintain the constant distance from the center. Now, how that surface would give you one equipotential surface, and if you think that, okay, let's make a sphere that has a bigger radius in the same way that I did here, then what you have is a bigger sphere that is enclosing the smaller one, and that one also has a constant potential, a smaller number like we did here for the equipotential lines. But in the 3D space, the way that we generalize lines is by thinking about surfaces and spheres for point charges in particular. So there is a way that you can generalize the equipotential lines to the equipotential surface for 3 dimensions. It is very difficult, though, to show you an equipotential surface here on my 2-dimensional board.